name is Jake. I'm a software developer, software engineer at Filecoin. I work on primarily on the cryptographic proofs and like the Filecoin proofs that you may know about. But today I'm going to be talking about what cryptographic proofs are, how they're used in Filecoin, some of the scaling limitations we've come across with the current proofs, and potential solutions, and namely the Halo 2 proving system, which is currently being developed by the Electronic Coin, or like ECC, and in collaboration with us and the Ethereum Foundation, meant to try to get it to a production-ready state where it can be deployed on like Filecoin and maybe with Ethereum and Zcash. And what are cryptographic proofs? They are not what you would typically consider to be like a traditional mathematical proof. Like for example, like there will be a proof statement, a thing that you're proving, and then you'll follow like a logical sequence of lines that like have to be logically consistent with each other until you get to a proof of the statement. And that's not exactly what a cryptographic proof is. But what these traditional proofs are, they're secure, like because they're logically consistent. There's no randomization in it, like meaning they're deterministic. They're non-interactive, so they're just like static proofs that you just read, anyone can read. They involve no interaction, and you just follow line by line. But sometimes those can be cognitively complex. There could be like a lot of logic in each statement, basically. And they're not super efficient, and they're more written linguistically for humans and not computers. That's not what a cryptographic proof is. A cryptographic proof or a cryptographic proof system, or just a proof system that I'll call, there are protocols that will allow computation to be outsourced to someone else. So if there's like some computation, just like some function with inputs and outputs, a verifying party can say, okay, we want some proving party to run the function on this set of chosen inputs. And then the prover has to prove that they ran the computation correctly, and they give you an output. And these cryptographic protocols, they allow for provable computation. And a very interesting thing about these cryptographic proof systems is that you can verify proofs from them faster than actually doing the computation yourself. Partly why that is that they're probabilistic, meaning that the verifier has access to some randomness, which they can exploit for fast verification. But that also introduces a small probability, a very small probability that false proofs will pass verification. This is one of the main differences with like a traditional mathematical proof is traditional mathematical proofs, they're static, they're deterministic, meaning that like if you follow line by line, you will always get to whether the proof is true or false. Cryptographic proofs, they're probabilistic, so there is a small chance that verification doesn't, or that false proofs verify. Partly how this is done is that like all of the logical consistencies or logical lines that would be in a mathematical proof, they're just all compressed into like a single arithmetic or algebraic statement, or just like function or equality sometimes, or polynomial or something. And then the verifier checks or like asserts that some condition on that algebraic statement is true, generally using some source of randomness. And like an equality will hold with some probability if the statement is true. Another part of what makes cryptographic proofs a little bit different than traditional proofs is that they're written for satisfaction problems rather than evaluation problems. By evaluation problem, I would mean given some inputs, follow these exact steps to compute the output, where you're actually evaluating the function line by line. A satisfaction problem is more along the lines of given some function and given some inputs, I, the prover who's proving like some computation, know some set of values that I could only know if I performed the computation correctly. That set of values they're private to the prover, and they're called the witness. So for like example, if you have some value A, maybe some input A, and you want to prove that you know like its multiplicative inverse, like the prover would like witness some value W and show that A times W is equal to 1. instead of actually going through all the arithmetic steps to compute the inverse of an integer, which would be an evaluation problem. And you get the benefit that a lot of arithmetic computations are easier to verify than to actually compute themselves. So for example, like verifying a multiplicative inverse takes one multiplication because you take some value A, some value B, you check if they multiply together to get one. That's a lot easier than actually computing a multiplicative inverse of an integer. And they have a property, or satisfiability problem, or evaluation problems can always be transformed into like a corresponding satisfiability problem. So these cryptographic proofs, they're not actually like evaluating things like line by line as you maybe would see in like a computer program or something. They're these satisfiability problems where you show you know all the values to make the computation true. So kind of this is a high level diagram, proofs for general computation. Cryptographic proofs, they can be computation specific or they can be for general computations, which generally is any arithmetic computation, but there can be more operations. And generally how they work out, and maybe it's not for every proof system as clearly delineated as this diagram, but you start with some general computation, like whatever that could be, like computing a hash function or I don't know, inverting an integer or whatever arithmetic program you want, like saying that like maybe I know the roots of some polynomial. You start with some general computation, F, and then you transform it into an intermediary representation, which is interpretable by the proof system. And usually a proof system will say like, okay, we're going to work in like this sort of hardware model, because it's not like a computer already has its hardware model, but like the proof system, in order to interpret computation, it has to have like its own model of how hardware works. And usually that's like a set of instructions. For many like arithmetic computations, the hardware model is you have addition and multiplication are your arithmetic operations. Then you have like your integer type, and those can be basically fed into each other, inputs and outputs to instructions. And that would be kind of like the hardware model. And then once you've kind of modeled your computation using like this hardware, like integers and addition and multiplication or whatever else, you want to write your computation as a satisfiability problem, which is like, okay, to do this computation, someone doing it correctly would have to know some subset of values throughout the computation as it runs. That would kind of be like if a program's running, maybe the person who runs it correctly would always know like what certain registers in your processor would hold, what certain values in the processor would be. It'd kind of be like that. And then once you have a satisfiability problem and it's using like operations and integers or whatever type of numbers the proof system wants you to use, then you convert it into some sort of algebraic statement or algebraic form. Here, for example, I have like a matrix times a vector, then a product of that with a matrix times a vector, and then you assert that that's equal to some other matrix times a vector, W. That would be like one sort of algebraic form that you can put these in, like matrix vector multiplication, and then you assert some equality. Sometimes it has to do with polynomials. But there's some algebraic form that these proof systems that a certain proof system will operate on. And then the proof system itself, it defines like how do you use this algebraic form to like prove and verify proofs. And then also cryptography is used to enforce that the prover has actually behaved and done the protocol correctly. In reality, the proof system kind of sets some of these things. Sometimes it doesn't. It's not just as clear cut as the proof system gives you a prove and verify function. Like sometimes it may say exactly what kind of satisfiability problems are allowed, what the hardware model is. And usually it sets like what the algebraic statements are that it ultimately will work on. There are many different types of cryptographic proof systems. And one of the most common are called Snarks. And that stands for succinct, non-interactive arguments of knowledge. Succinct means you have fast verification. Non-interactive means that the prover and verifier don't have to interact. The prover just can send the verifier a single message, the proof, or just publish it publicly, and anyone can verify it, or the verifier can verify it. Arguments of knowledge. Well, argument means that the proof system or the proof itself is secure against a cheating prover, unless when the prover is computationally bounded, like in modern cryptography, most cryptographic techniques are secure when you assume like there's some bound on the prover's or the cheater's computational ability or resources. An argument means the same thing. It's a proof system that's sound unless the prover has some like extraordinary, basically impossible computational power or resources. Then if knowledge means you're proving a satisfiability problem, it means that the prover knows some secret values or some values that they could only know if they ran the computation correctly. So these snarks, these cryptographic proofs, they can enable decentralized storage, which is what Filecoin is. Filecoin is a decentralized verifiable storage network, meaning like anyone can join to be a storage provider. And they offer a service of storage, and they have to prove that they have the resources to offer the service, and they have to prove that they're storing people's files, and they have to prove that they've like maintained people's files. And there's also a public ledger, which basically keeps the state of the network. It says like what storage providers are currently providing what storage to what clients, and how much resources that they have available. What's nice about Snarks and why they can be used in Filecoin is that Snarks have small proofs and efficient verification, non-interactive proofs, meaning like the verifier and prover don't have to communicate, which is really useful in a like public ledger type system. And the verifier and prover, they don't have much additional overhead because of these proof systems. Like the prover still has to do like the computation that they're proving, but the proof system doesn't add much onto that. And fast verification, yeah, it just helps for people who are verifying the proofs that are generated by storage providers. This meme, it shows Drake on the left-hand side saying, in a decentralized system, I don't want people like living in the data center basement, maintaining like a state of the network. Like we don't necessarily want, we want maybe to automate these processes. If you have like storage providers constantly coming on and offline, it would be kind of a pain to have like someone living in the basement of everyone's data center, like ensuring that there's like a certain amount of storage available, and it would just be hard to do that in human space. But you can use Snarks to automate a lot of that process, and that's a lot of what Filecoin has done, figuring out how to use Snarks to automate these processes. So Drake is saying, yes, Snarks, no, some guy living in the basement of your data center, monitoring your resources. But there are many Snark systems. There's, I mean, really over the past decade, there has been what many people call an explosion of Snarks improving systems. Like some of the most common ones are like Pinocchio was like an original that really laid the groundwork for a lot of these. Grot16 is a very popular one today because it has succinctness and fast verification and low prover overhead. There's just a lot, and they keep more and more developed every single day. But some of the properties that you might, at least that Filecoin looked at, and that you would look at if you were trying to choose one of these proving systems, is like proof size, verification time, which usually are highly correlated. Does the proof system require a lot of resources from the prover on top of the computation that they're proving? What sort of like mathematical operations does the proof system require in proving and verifying? Because some mathematical operations are really expensive. So even if there's like a small number of these operations, they could still be really, really expensive. And that would be like something like FFTs, which would like multiply polynomials, or you just basically use for multiplication. But also certain like elliptic curve operations are really expensive. So you basically have to weigh out the cost of like the types of operations you're doing and the numbers of them would factor into your overheads on the prover and verifier side. But also you could look at potential optimizations for those operations, which is something that Filecoin engineers have done a lot of. Like, how do you optimize these proof systems beyond, like, in practice? Many cryptographic proof systems, and Snark specifically, they have some setup procedure. Sometimes the setups are specific to the computation being proven. Sometimes there's one setup for all computations that will be proved. Sometimes you can have just like, you can keep updating the setup as you go, like maybe to ensure security or to add on to it. Or then there are transparent snarks, which are relatively new, but they don't require the setup procedure. In certain ways, they may be less efficient than current snarks, but yeah, I'll get to that in a little bit, but they are very interesting and they don't require this like big costly setup procedure, which is usually called trusted setup. Yeah, and it allows you more flexibility in what kind of things you're going to be proving, because maybe you don't have to do a setup for every single like proof that you're doing. And sometimes if you're doing like a computation specific proof, or like you have your proof system is computation specific, or you may be limited by the size of computations that you're allowed to prove, because like if you have run trusted setup for whatever, like proofs with like 100 multiplications, and then you come and say, I want to actually prove something with like 200 multiplications. Well, you can't do it. You have to do another one of these very costly setup procedures. So that's where transparent Snark systems would be really helpful. Then when you're choosing a Snark or cryptographic proof system, you want to think about its hardware model, or how it internally, or how you represent just a general computation using like the operations that the proof system like allows you. So for example, like I guess if you have a computation that's using like maybe bits, like if you were doing like a SHA hash or something, and you want to prove something about that, but your proof system, it uses like integers and doesn't have like bitwise operations or binary operations or Boolean logic. Well, the transition from bits to integers and like arithmetic operations in the proof system's hardware model, you may get a big blow up, and it may not be the right Snark or proof system for you. Also, you might want to consider what is the aggregatability. I'll talk more about this later with proof systems, but it basically allows you to batch together proofs. Maybe you can prove multiple proofs in a single one, or in a single proof, or maybe you can verify in batches. And then I guess existing developer tooling is also really important around the Snarks. Like there's only a handful of these that have actually been done in practice and have like support from like communities or companies. And they're pretty complicated. So having like a community with like programming language support and like libraries that are usable is also a big factor in like choosing a Snark, because it's a lot of work to try to create a library that does all of it, the things necessary from scratch. And Filecoin chose to use the Grot16 proving system, which is one of the most popular Snarks right now. And it's popular because it has small proofs, which means very fast verification, and low prover overhead, and yeah, there's a lot of developer tooling, a lot of people use it. I think I'm running low on time, but the way Filecoin proofs is, it's a decentralized storage network. Is basically you have a client that says, I need file storage. A prover or storage data center person says, I'll store your file. And then they have to prove that the prover has to prove that they're storing the file. Then the client says like, it needs some proof that that the file has been maintained in the data center. And those are called POREP, proof that like a file has been stored, and proof of space-time, proof that the file has been stored over time. Filecoin's been producing many proofs. I'm not going to go through all these metrics, but we create a lot of proofs is essentially the big takeaway. The limitations of the current Snark system in Filecoin is that there are a large number of proofs, and that creates a bottleneck because every proof has to be validated before it's included in the public ledger. And that's a bottleneck on the network and like growth and onboarding storage because it takes a little bit of time to verify these. And if you're creating a ton of proofs, then it may take too long. Like it will slow how fast things can be included in the public ledger. Also, you have these per statement trusted setups with Grot16, and that limits you to what computations you can do and the size of computations. So the solution that I am most familiar with, that we've been working with, and we've been working with the Ethereum Foundation and ECC Zcash developers, is the Halo 2 proof system. We have many solutions to like some of these Snark scaling issues. But Halo 2 is the one that I've really been looking at. And it's a new proof system, not Grot16. But it has a transparent setup, which means that you don't have a trusted setup or setup. So you can prove any statement that you want. You can prove like anything you want. You're not restricted to like one or two things that you're proving without a trusted setup. And you get what's called proof recursion. And this is going to factor really highly into the potential scaling solutions in the future, at least for Snarks. And it means that you can create proofs that verify other proofs that have been proven. So if so you could create one proof that maybe verifies like 1,000 other proofs and then just post that to the public ledger. And essentially it kind of makes a tree structure to my understanding of this so far. Zcash is currently like implementing this and getting it down, but there are papers and stuff about it. Halo 2 also has weaker security assumptions, meaning it doesn't assume as much as like our current proving systems, like Grot16. Like it has, it assumes less about the environment. Usually that means there's more security, or they're a little bit more realistic maybe if you have weaker security assumptions. And you get some new arithmetic operations you can do like within the hardware model of the proof system. Like namely, you can have like lookup tables. Like you can basically do like dictionary lookups or like hash map lookups, which is pretty cool. And that's not something that I know of in other Snarks. And you have other arithmetic operations like you can define like your own arithmetic operations for computing specific polynomials, which is interesting. But yeah, the main thing that we're really interested in is this proof recursion, where you can offload storage of like maybe thousands, maybe unlimited number of proofs into a single proof via proofs that verify other proofs. And this is currently in development, and yeah, working with ECC and the Ethereum Foundation on it. Yeah, Zcash has done a lot of work. They have papers on it. They are leading the development of the libraries in Rust. But everyone is really excited to get it fully developed and production ready and deployed possibly in various public ledger type systems. Yeah, that's it for me.